visual art. Robotic arms not just used in the industry factory floor, but these days, have you watched a movie called Gravity before? It's this robot behind it to create that weightlessness effect. Yeah. So the part about Sandra Bullock flying away, right? That one is just totally created by this robotic arm. It's just moving from one side to the other side, and all she does is just doing this, flying out into space. So there's a lot of wonders that the end effector or this robotic arm can do. It's all about the path planning trajectory. I need to do some definition first. What are path? What is path and what is trajectory? Both of them are, in some sense, we're trying to control the movement of this end effector to move from one position to another position. This is all our controlled motion. How do we go about controlling it? You'll be looking at displacement or its position, velocity, how fast it moves from one position to the other position, and the acceleration, how much it will accelerate from one position to the other position. So path, some of you looking at the word path, trajectory, thinking that, hey, this sounds like, as an English word, I thought they are the same. Path is movement independent of time. We don't consider time, how much time it will take. It's just that displacement that it would take. Trajectory is when you need to consider the amount of time. There's this additional information where each point of the path must be reached. So at a certain point of time. So that is trajectory. So we'll be looking at a lot of things relating to velocity, acceleration. If you have been if you are able to recollect what you have learned before in kinematics, if you were to differentiate displacement, what do you get? You get velocity. So you get to see that again today. And if you differentiate velocity again, then you get acceleration. So the thing that you're going to be hearing today hinges a lot on this concept, right? From position to velocity and then to acceleration. If you have an end effector, so in the Lingman word we call it the robotic arm, but really it's an end effector. So over here you get to see three links. So the three links will be this one, that one. Well, this one's not moving, so that one, and that one. So it's able to move in 3D space from position A to position B in that way. And normally we need to define how you move from position A to position B. It's not just defining that 2 points. You can do so, but you lose a lot of information to tell it what to do in between from position A to position B. Now, why is this intermediate point definitions important? That's because sometimes you'll face a problem of the robot may need to pass from position A to position B. If it's going to be in a straight line, then you'll pass through itself. It's like that. So in that case, you need to define another place for it to go to. If you just define A and B in that way, then you'll just go from A to B, and then you'll crash into itself, or you get an error that's returned because it couldn't pass through itself. So in order for it to go from A to B, then what is needed is that you define another position
out there. So they will go from A to A prime and then to inner position B. And you will avoid crashing yourself. There's also another popular problem in robotic arm or end effector. That is, this robotic arm has been making that path, that straight line path on one side of it. So drawing that straight line in that side. And in order for it to reach further position, you need to turn around and then continue that position, continue that path. But that turning around requires time. So what's going to happen is that it's going to do this and then turn the other way around. It's not possible within the time frame that's given to it, because you'll be defining that it has to travel from position A to position B within a certain velocity, within a certain acceleration. So for it to do that drastic change, turn around, it's just not possible. So if you want to reach from this position to the other position, you will be able to do some of the path, but then it has to rotate around. So in order for it to be able to accomplish this task, then you have to define intermediate points again. Right? So later on, you get to see how we go about designing some of the intermediate points.
But before we go into that, there are two things that I need to define. Two ways that we can let this end effector know how to move about through space. Two techniques. The first one is joint space description. The second one is Cartesian description. It sounds big words, but really is kind of quite simple.
Why is it simple? Because if you think about it, if you want to define where this end effector is in 3D space, how do you go about defining it? Maybe you say that, okay, I want 3D space, right? So if I want it to be at this point as x, y, z, with reference from an origin x, y, z over there, then I define that point, and then you will try to go to that. This method is called Cartesian description. So you describe the x, y, z coordinate in 3D space. Tell your robotic arm or end effector where to go to 3D space. That's one way to define it. Another way to define it is that, how about if I don't define this x, y, z, I'll do it by defining what is my end effector length angle. So for this, you can see my arm is kind of like three links here. This part, and that part. So for this part here, that is going to subtend at a certain angle. The next arm is going to subtend at another angle, and this one at another angle. So I can go about just defining this, because embedded inside this link will be motor. So I'll tell my motor, go to that certain positional angle, and then you go there, and then I'll arrive at the same x, y, z coordinate. This method of commanding where the joint position is going to be is called joint space description. So you have two ways to define it. What are the differences? Well, the Cartesian form of defining it, you can see that at the end of the day, in order to be able to figure out where is your x, y, z coordinate out in 3D space, you would still need that end effector arm position. So there's a backward calculation that's necessary. So in order for it to go to that x, y, z position, sometimes there's more than one way of defining it. Same point, but I can move a few ways to define it. So there may be quite a few solutions, and in order to calculate all the possible solutions and which one to avoid is computationally more intensive compared to using the method of joint space description, where you just define the linkage angle as subtended with respect to the ground, for example. So these are the two differences. Your joint space description will afford you a more precise motion. Although if I say this first link at 30 degrees, that 140, and this one at 10 degrees, it's hard for you to imagine in 3D space how this is going to be positioned compared to if I have an XYZ coordinate. So your joint space description is harder to visualize, although computationally it's easier to compute where is the position that the motor needs to rotate to.
So this some of the this one of the disadvantage. And for joint space description, if we are going to travel from in a straight line from A to B, we can divide that straight line into smaller number of proportion. So what that means is that if I want this to move from this position A to that position B, what I need is that I will define how this between this A and B, how I want to divide it into smaller number of proportion in order for it to move step by step into that new position. So this is easy to define using the angle. So what I need to do probably is just to say that angle that is 10 degrees, let's increase it to 11, 12, 13, 14, 15 degrees, and then I'll arrive at point B. So you can do that in steps. And you need to do this path planning in steps, or else it's going to hit something that you may not know, because sometimes you have two robots that's working together and they may intersect each other's path. So you need to do that steps of that incremental steps as you travel from point A to point B. So you can see that the Cartesian space description is computationally more complex. It requires faster processing power compared to your joint space description. And actually, it's difficult to ensure that no singularities would occur. These singularities just mean those cases that I spoke about. All right, this is the point of singularity. It's actually a word that's used in physics. Singularity just means a point of abnormality. Sometimes used in gravity, the Einstein's theory, black hole singularity, where you have the mass of the object as infinite, so there's a point of singularity. Anyway. Okay, let me give you an example of how this robotic arm is going to move. We're going to do our definition using the joint space description. Since the joint space description is less computationally more intense, there are a lot of end effectors out there, some of what I've already played in the video. KUKA is one of the major company. Bot and Dolly seems to be turning into the cinema industry to do their work. In either case, the robotic arm you can define its angle or its Cartesian coordinates. Nowadays, actually, the computing power is actually powerful enough to do all those work. So I have this very simple arm, robotic arm over here, where I'll define this one as my lower link and that one as my upper link. So what I'll do is to use my arm to represent that, so that you can see this one is my lower link, and that part here, one straight element, is my upper link. So in order for me to move from position A to position B, what I can do is to distribute this motion into steps. And how am I going to do it is that, say for example, I can only move, my motor can only move in step size of 10 degrees per signal. So whenever I give it a signal, it can only move 10 degrees resolution. So what's going to happen is that this lower arm will move in steps of 10 degree, 10 degree, 10 degree. And while it's doing that, my upper link will also move as well in steps of 10 degrees by 10 degrees by 10 degrees. So because of this fanning from position A to position B, you'll find that what is shown in this case, my lower link can accomplish its final position just by 1-2 steps. And after you arrive there, then you will stay there. And then in the meantime, my upper link would move in steps as well of 10 degrees, 1, 2. And then since it's not there yet, you continue to move 10 by 10 by 10 degrees. So what is going to happen is that this part over here, you can see that this lower link doesn't move at all. So the lower link stopped. And the upper link will continue to move in steps of 10. So this table over here, now this timeline is what I provided. It's not really given in the classical notes, but I thought it's easy for you to visualize. So we start by having this angle alpha at the lower link at 20 degrees. And beta is taken from this axis of the lower link, measured from this, 30 degrees. Right? That's beta. So alpha will start to increase from 20, 30, 40. So 20, 30, and 40. And then after that, you will stop. And beta will continue from 30 degrees, 40, 50, 60, 70, 80. That's what you can see over here in each of the time step. So it sounded like, yeah, that's a fair robotic movement. Kind of like it moves, and this one will stop, and this one will continue to move. But in reality, actually, this is not an elegant way of moving this robotic arm. Besides being elegant, there's also the practicality of it. Because if you were to move this robotic arm, you would want it to be all moving at the same time. Right? And then stop. Compared to you do this movement, yeah, and then this thing stop, and this whole thing is supporting how this arm is going to be moving. And you have this overhanging part of it. Right? So it's better to have everything that's moving together, fanning out in that way. So another way to do this is that why not this lower link, what we'll do is to have it move in smaller steps. So how about moving them in smaller steps? So that smaller steps would be synchronized together with the upper link, that as this were to move, it will all move together. So we can distribute that initial position to a final position in greater amount of steps, such that this arm here can catch up. And then the whole arm will move in a very elegant way together. Yeah, that. Okay. But then there's another problem. This problem is that the robotic arm moving from position A to position B. Why not we have this position A to position B movement to be in the shortest path possible? What do I mean by that? You can see that this arm that's fanning across in that way. This actually from position A to position B is not the shortest path, because the shortest path is drawing a straight line in between. So why is shortest path that important to us? That's because you wouldn't want to move from position A to position B to go somewhere else and then come to position B.
you want that shortest path possible so that you save time. You just move from A to B in one straight line. So if you want to have that kind of movement, then you have to redesign how your robotic arm is going to move. So I have one setup over here. I used to do a lot of camping, so I have this thing that I use for the tent. So what I want to do is to demonstrate this robotic arm. Okay, so this one such arm. So imagine I want this point over here to start off at position A, and then I want this point here to move to a point, position B, that's directly vertically up there. Right? For it to do that, you can see there's a combination of this lower link and upper link angle. So in this case, this angle here, subtended, maybe is about 300 degrees, and the one that's at the bottom with respect to the ground, that one's almost like maybe 85 degrees. So we start at this position, and then what I want you to notice is that as I travel in a straight line upward, I want you to see this arm over here. Just turn it this way so that everyone can see. If you can't see, because today's class is flat for me, so if you can't see, you can stand up. What I'm going to do is to move this vertically straight up, and what I want you to see is this angle over here, this angle. I want you to see if it's always decreasing or is it increasing that angle. Okay. So I'll move it up in a controlled way, straight. You can see that the angle is getting smaller, and it's going to go straight up. Now that angle has changed. It's going up there. So it's decreasing again. It's decreasing again. And then it's increasing. So what I want to show you is that this robotic arm angle over here, it's not necessarily that it must be always increasing or decreasing as it moves that the end part of the end effector from one position to another position. So you have to look at how is it structured, what is the length of this, in order to figure out how this angle is going to be moving, because you'll be programming this angle. That programming of the angle comes about in adjusting how your motor that's controlling is going to be moving in that position, angular position. So this can be shown in the following slide over here. So you can see that from the angle, we start with angle 20. So the one that's highlighted in red is where our starting point is. The one that's in blue is where it's going to end. So it starts from 20, and then you would decrease, and then you would increase, and increase, and increase. So it moves from backwards a little, and then before it moves forward. Whereas for your angle B, you can see that it's always increasing. So the step size of how many degrees that this link is going to move, that step size is defined by how much your stepper model, what is the resolution of your stepper model. So the higher resolution your stepper model has, then the better resolution, this angle resolution, you will obtain.
So we can see now from position A to position B, it's moving through 1, 2, 3, 4, 5, 6 in this manner, in a straight line. So we evolved from how this robotic arm used to move at the lower link, and then you will stop, and this upper link continues to move, to equally distributing that angle, to now it's moving in a straight line. Yeah. But it's still not good enough. There's something about this straight line that's undesirable. What you could see over here is that from 1 to 2, these are equally distributed. Right? They are equal distance. And in fact, depending on the resolution of your encoder, sometimes they are not totally equally distributed here, because there are certain angle that's just one more step size from your stepper model, and then it makes it the length is not really equidistant. So, but besides that, there's also the part about how this robotic arm would move from A to B in equally distributed distance, and that is why not?
Why not, as we move this robotic arm from A to B in a straight line is desirable. Why not that as we move it in a straight line, the first part of it will accelerate it, and then somewhere in the middle, we'll make it such that it moves at a constant velocity. And then toward the end part of it, we'll have deceleration. Right? So you have seen a lot of robotic arm movement that turn out that it moves in a very smooth manner because there's an acceleration phase, and then you'll move at a constant velocity, and then there's a deceleration phase, and then it will stop. If it's not moved in this way, that means it's going to be energized suddenly, and then it moves in a constant velocity, and then stop suddenly. Right? So you have seen a lot of old movies here where the robot would move this way, and then that, and then that, and then that. That shaking is bad. Why is it bad? Because you're stressing your motor. Right? It's not only it doesn't look good, but we can do better than that. We can slowly accelerate it and move it slowly, and then decelerate. And then you don't have to feel that jerk, because whenever you have that jerk, that means your motor is under stress. This is not good. So that means we need to refine this straight line motion again. And how we're going to do it? We're going to have different segments. In the beginning of the segment, we'll have the acceleration phase. And then we have this part here that's constant velocity, and then deceleration. Now this can also accommodate your
your rougher resolution from your stepper motor, because then your stepper motor wouldn't have to kind of like have this equal distance distribution. So you can accommodate some of this error over there in the acceleration phase. And then for the constant velocity, you can see that this kind of more or less equal to each other. Sometimes it's actually hard to achieve perfect equidistance here. But then the result of it is that your motor will not be under undue stress. So that's good for your motor. Good in the sense that your motor can last longer if you have the acceleration and deceleration phase. So let's have a look at how we go about dividing this. And I kind of want to highlight your Newton's equation of motion. If you remember the three equations, Newton's equation
of motion. So you have this part here, final velocity equal to initial velocity plus acceleration multiplied by time. Saw this before in your earlier education, where you use that to calculate what is this object that's flying through space, and then you want to figure out what is that final velocity, that sort of thing, or you want to find out what is its acceleration at a certain point of time. You'll make use of the Newton's equation of motion, the laws of motion. So this is the displacement or the distance traveled equal to your initial velocity multiplied by time, this acceleration, time squared divided by 2, final velocity, initial velocity, acceleration, and your displacement again. You may have seen this x as s, represented as s, because s would be talking about your displacement. But in this case, the notes
is using x, so I'm keeping to be consistent with that. So let's have a look at how do we get to this part here. So you would divide, what we're going to do is to divide it on the basis of this until we reach the constant velocity. So we're talking about this acceleration phase over here. So if I look at this, x equal to ut plus at squared divided by 2. So my initial velocity, that red line over there, says that my initial velocity is equal to 0. So what I'm going to have is x is equal to at squared divided by 2. So that would tell me at any position, I can calculate that based on this acceleration that you experience. So let me find out what is then that final velocity. So final velocity, v squared equal to u squared plus 2ax. And again, my initial velocity is equal to 0. So equal to 2a, and x over here will be at squared divided by 2. So if I just simplify that, I get a squared t squared. So you square root on both sides, you get v is equal to at. Back to where we are over here. V is equal to at, where u is equal to 0. So the Newton's law of motion, they are consistent with each other, and you can use that to do that simple calculation. If you want to calculate what's the acceleration, or if you want to calculate what is the displacement. Now this motion for the robotic arm is still not perfect yet. Right. So we have moved from a few different kind of configuration, slowly improving it to the point where the robotic arm is moving in a straight line. And not only is moving in a straight line, but you have the acceleration phase, deceleration phase, constant velocity phase, and then deceleration phase. But this is only from point A to point B. If you want to move it from point A to point B and to another point, that's point C. And you can draw a straight line that's that way and that way. What's going to happen is that if you're to design your robotic arm to move in this way, right? Point B is A, B, and C. You're going to have the acceleration phase and then constant velocity, and deceleration phase, stop, and then acceleration phase, and then constant velocity and deceleration phase, stop. This wastes time, right? And why do I need to move to B? That's because maybe you want to avoid something, right? So for every of this motion, you want it to be as seamless as possible, even though it's changing its direction of travel. You want it to be seamless. You don't want it to accelerate, constant velocity, decelerate, stop, and then accelerate, constant velocity, decelerate, stop. You don't want it to be that way. You want it to move continuously without stopping at the intermediate position. So if you want to do that, then what can we do? We can have what we call a blended trajectory. And I'm going to use these two figures to show you that.
This figure and that figure, they are actually a little bit different here.
This position B here is the same as this position B over here. And then A and C. A and C. B prime is actually a little bit lower than your position B. And B prime prime, or double prime, is a little bit above the position of D. So B prime is slightly lower, B prime, double prime is slightly higher.
What we're going to do as we move from A to C is that instead of going to B, we'll let the robotic arm to pass through B prime. Right? Now, how do we do that? What we're going to do is that we're going to accelerate it and then have it move through a constant velocity. And then if that B point is a sharp angle over there, if it moves through as a constant velocity, it's going to experience jerk. Right? So it's just like if I walk one straight line, and if there's a change in direction at a constant velocity, you're going to experience like a sudden turn. So you can't really move in a straight line to change your direction suddenly at a constant velocity. You have to decelerate first, and then come to rest before you turn, and then go on to another trajectory. So what if I want to maintain that constant velocity as I turn? So what you could do is that instead of that sharp corner, you take that smooth blend into the other path, right? In a constant velocity. So you don't experience that sharp corner, because that sharp corner to a robotic arm means that you experience a jerk. And that jerk will reduce the lifetime of your starting moment. So that little arc over here, so if I zoom here, that little arc over here is what it's trying to do. As we move from this position A to, instead of passing it through B, we have that constant velocity moving in that way through B, and then it changes the direction to move to the point C. And in that case, you wouldn't have that jerk coming in. This point, B prime, is what we call your intermediate point, right? Your intermediate point. But there are certain applications where you need the robotic arm to pass through B, right? You don't want it to go through B prime. Going through B, your robotic arm will experience jerk because it changes its direction. So B prime is good. But what if I have an application that says that I must pass through the path B? So if you have that case, then what you need to do is to design another point, intermediate point, that's called B double prime. And that B double prime is where you have that jerk that's coming in. But in order to avoid that, you actually have this smoother curving point, intermediate point that resides where B position is. Because we are trying to define the robotic trajectory must pass through the point B. So if it's going to do that, then you design that B double prime point to be slightly above it, so that you move smoothly arcs through your point B that you define you must pass through to continue in a constant velocity to the next new position, C. So I have a slide, I think, to kind of like put everything together. This one. Let's see.
So what I've done is just to move that. You can see the relative position of all of it. Go back here. Alright, so point B is here, B prime is below it, and B double prime is above it. So if you must pass through point B, then you design that B double prime there, so that you will move through in a seamless manner at a constant velocity, and then you wouldn't experience too much of a jerk. So the whole idea of this robotic arm is just to make sure that you'll move through this 3D space in a seamless manner without any jerk, so as to prolong the life of your motor, your stepper motor, by having acceleration, deceleration phase. And if you need to move it through various different points in your 3D space in a constant velocity, that's how we go about designing some of these intermediate points for you to move through. Now the next few slides, they're going to be quite a fair bit of mathematics, and I want to start that by kind of like putting things into the right frame. I want to start by this line that you're very familiar with. Y is equal to mx plus c.
If you look at this line, could you see how many unknown constants are there in that straight line? Y is equal to mx plus c, unknown constant. Which are the unknown constants in this case? Your m is one of them, and then the other one is your c. So m and c, they are unknown. Two unknowns in a straight line.
So M, C are unknowns.
And if I were to ask you this straight line over there, is it a first order, second order equation? It's a first order equation, because second order means that your x will have a square. Your third order equation means that x to the power 3, and then you have subsequent x squared, x and a constant as well. That's your polynomial general equation. So in this case, this is also a polynomial
General equation that we call it the first order polynomial equation. Y is equal to mx plus c. So hence, for any first order polynomial equation, generally you would have two unknowns. Those unknowns will be m and c. So hence, in order for you to find out two unknowns, how many boundary conditions do you think you would need? You would need two boundary conditions. So a very easy boundary condition to pick up would be this point, that point. If you know these 2 points, then you can solve for those two unknowns. So you have two boundary conditions. That's good. How about if we have a case of a, what do you call this kind of curve? Quadratic. So it's not linear, but quadratic. So for a quadratic equation, how many number of order polynomial do you think it is? This is second order. So second order polynomial equation. And in this case, how many unknowns do you think there will be? So this equation will be y is equal to ax squared plus bx plus c. How many unknowns? There will be 3. A, B, C over there. So 3 unknowns. And how many boundary conditions do you think we'll need? You need at least 3. So maybe this point, that point, that point, or any other 3 points. That will give you the 3 boundary conditions. So now, let's have a general case. That curve. Where I call this my nth order polynomial equation. For nth order polynomial equation, how many unknowns do you think we'll have? It will be n plus 1 unknowns. And hence, how many boundary conditions do you think we'll need in order to solve this nth polynomial equation? That will be n plus 1 as well. This provides the stage of where we're going to go to, where we talk about the nth order polynomial requiring n plus 1 boundary conditions.
So now I'll just kind of like randomly give you a small little quiz. If I have 4 boundary conditions, how many number of order is my equation, polynomial equation? 4 boundary conditions. You'll be a 3rd order, right? So it can be asked to you in that way, or it can be the other way around. If I have a 5th order polynomial equation, how many boundary conditions do you think I can use? It 6. So now something a little bit more challenging. For my robotic arm to move from one position to the next position, just focusing on this lower link, from this position to the next position, how many boundary conditions do you think I will have? You say 2 probably come about when you define what is its initial position and what is its final position. That will be your boundary condition. But we haven't talked about this velocity yet. So if it moves from the rest state as this first position to the next rest state, second position, how many boundary conditions do you think you have? You have this initial position as 0, this final position as certain angle, initial velocity as 0, final velocity as 0, comes to a rest. So there are altogether 4 boundary conditions. For 4 boundary conditions, this movement that's defined, which order do you think it is? It will be a 3rd order polynomial. Alright? So that's how we go about defining how this robotic arm is going to move. It will move with a 3rd order polynomial behavior. Alright? So at any point of time, we'll know what is its position, what is its velocity, and then later on we'll use that to calculate what is its acceleration. So we'll start off with that 3rd order polynomial.
It's written over here, but what I'm going to do, because it's really reduced form, and I like to sketch some figures, so I'll just do my solving right next to it. You can see if you want to write after me, or if you want to just fill in the gaps in between. And I find that this term over here, d theta ti over dt, is a little bit cumbersome, so normally I'll write it just in this way with a dot at the top, because that represents the rate of change as well. So I'll be using a lot of this theta dot dot. Theta dot here means your angular velocity, and theta dot dot will be your angular acceleration. So let me sketch that link. So I have that lower link. This is my lower link. And in the axis of y and x, in my Cartesian or xyz coordinates. And it's subtend at an angle theta. And I would say that it will start, this angle over here has a time behavior, all right, because it will move from this position to another next position. So at any point of time, it's at a different position. So if I were to consider theta at time at initial, so I there refers to initial time. Later on, you see TF, and F stands for final. So you will have an initial angle that I call theta I. And as it moves to the final position, you will have a final angle at time TF. So this Ti and TF is your initial time and final time. And I can represent it, this theta TF as theta F in short. So we would know that Ti is when we can consider time equal to 0 seconds. So that means we can write theta at time equal to 0 is equal to a certain angle theta I, certain initial angle theta I. So we have seen before that this link will be governed by a third order polynomial. So we can start by assuming third order polynomial, where we have theta t equal to, I'm going to write it in this way, C0 C1 t C2 t squared C3 t to the power 3, third order polynomial. It's not using x. Right, just now the example that I gave you is y is equal to mx plus c, but in our case over here, we're talking about the movement with respect to time. So you have a third order polynomial in the time frame t. So let me list down all the initial and final boundary conditions. You have the initial and final boundary conditions. 4 of them. We can expect 4 of them. So the first one, when theta is at Ti, we have already written it down. That's equal to theta I. So we don't know what's that initial angle, but we just put that initial angle as theta I. And we know that Ti is equal to 0 seconds at that time. So this one I call it equation 1. This one I call it equation 2. And we also know that at this initial angle, or this initial time, when time is equal to 0, the velocity is also equal to 0. That velocity over there represented by theta I. So this is my equation, another equation. Theta at the final time, we don't know how much time it will take, so we just write it now as Tf as our final time equal to theta f. I call this equation 3, this is equation 4, and lastly theta I at t at final time equal to 0, equation 5. So you can see all these boundary conditions. They are altogether 4 boundary conditions. And hence, 4 unknowns to be solved later. 4 unknowns in theta t. So theta t is how your angle would move through with respect to time. Theta t is defined by this equation over here. So the 4 unknowns will be C0, C1, C2, C3. So because of 4 unknowns, we know that it's a third order polynomial.
So I've seen exam questions before that didn't really tell you how many number of order polynomial you expect. In your tutorial, I think it's given. It says, oh, start with a third order polynomial. So that allows you to know what is the number of boundary conditions. But sometimes the question is given to you such that it will tell you what are your boundary conditions in words. And then you're supposed to use that boundary conditions to know how many number of order polynomial you are having. So if you don't know this concept about third order polynomial for boundary conditions, then you wouldn't know how to start with. You wouldn't know what is that order of polynomial to start with. So please know this. Every year, this question, over 95% of students attempt. It's easy. Later on, I'll try to solve some example so that you can see that. For that, let's go for a quick break and then we'll be back in 5 minutes.